This is a review of question 3 on exam 3. A spring is initially compressed by a 50 Newton force, a distance of 7.50 centimeters from equilibrium by a 7.00 kilogram block of wood. The block of wood is released from rest and slides along a rough surface with a coefficient of kinetic friction of 0.350. The block is not attached to the spring and will slide away. Part A, find the spring constant. Well, they tell us it takes a 50 Newton force is required to compress the spring a distance of 7.50 centimeters or 0.075 meters. So we use the relation F in magnitude is equal to K times X in magnitude. And from this, we can calculate K. K is equal to F over X, which is 50 newtons over the compression distance, 0.075 meters. And we do that, we find that the spring constant is equal to 667 newtons per meter. In part B, we're asked to use the conservation of energy to find the speed of the block at the equilibrium position of the spring, x equals 0. So initially, the block spring system has energy equal to the compression energy. And then that compression energy, once the block is released, that compression energy is used up in the form of kinetic energy, but also gives up some energy due to friction. So then conservation of energy tells us that the work done by the friction will affect a change in the kinetic energy, plus is related to the change in the potential energy. In other words, the work done by the external force, the friction force, changes the mechanical energy of the system, delta E. So we can rewrite this as minus Fk times the distance. Let me call this distance delta x. And the change in the kinetic energy is equal to 1/2 mv final squared, where v final is the velocity when x gets back to x equals 0. And then we subtract that from that the initial kinetic energy, which is 0. Because it's at rest. So that's the change in K. And then we also have the change in the elastic potential energy. Let me put an E here to indicate elastic potential energy and not gravitational potential energy. There is a gravitational potential energy, but since the mass never changes its vertical position, the change in the gravitational potential energy is zero, so we can ignore it. Then we can write the change in the elastic potential energy as equal to the difference between the final elastic potential energy, which is 1/2 kxv squared minus the initial kinetic energy, which is 1/2 kxa squared. But xb is equal to 0, so this term is 0. And also we should note that delta x over here on the left-hand side is equal to the final position, which is xb minus the initial position, which is xa. And xb is 0. And minus xa is minus 0.75 meters. So it's equal to plus 0.075 meters. Okay, so we're ready to solve for the velocity v sub s because we know everything else. If I multiply this equation by 2, I get that minus 2 fk times the magnitude of xa is equal to mv squared minus kxa squared. Then I can rewrite this as v squared is equal to kxa squared minus 2fk times the magnitude of xa. xa, as we know, well, let's just go ahead and put in the numbers. K, we found from part A, is 667 newtons per meter. XA is 0.075 meters. We're going to square that. And then we're going to subtract from this the 2 times the friction force. The friction force is equal to mu sub k, which is 0.350 meters times g I see I haven't allowed enough room here. times delta x. Then we calculate the right-hand side and take the square root of it. We find that v sub f is equal to 0.147 meters per second. So that's the velocity when the spring gets to x equals 0. In part C, we're asked to use conservation of energy to find the distance the block will travel before coming to rest. That is the total distance from the starting position. Well, once again, conservation of energy can be expressed as the work done by the external friction force causes a change in the kinetic energy plus a change in the potential energy. If we're talking about the total distance from position XA to some final distance beyond XB, then the initial kinetic energy in that situation, since it's starting from rest, is 0, and the final kinetic energy is going to be 0 because it comes to a rest after this total distance, d. So we could set this term equal to 0. On the other hand, we could treat the problem as initially having the block at x equals 0, that is, the spring has undergone the decompression, and treat it from that point on, from this distance initially, call this our initial position, and this our final position. And we can find this distance and then add it on to the initial distance of 0.075 meters. And some of you did it that way. If that's the situation, then there is no elastic potential energy in the system at all, and it's just a change in the kinetic energy from whatever the kinetic energy is at position xb, which is 1/2 mv squared, where v is this quantity we found in part B. But I didn't do it that way. I treated it like the initial position is at XA, and the final position is whenever it comes to a stop. And so that's the total distance d. And in that scenario, the first scenario I just described earlier, the change in the kinetic energy is 0. Then I can write the work done by the friction force is minus Fk times this total distance d. And the change in the elastic potential energy is the same as the change in the elastic potential energy that we had in part B, and we found that to be minus 1/2 k x a squared. So then we can see that the minus signs cancel out, And we can solve for d. D is equal to 1/2 kxa squared over the friction force, which is v sub k, times the mass, which was 7.0 kilograms, times g. And after writing this down just now, I realized that in my earlier calculation up here in part B, I should have had the factor of the mass in here. I apologize for that mistake. But you must have this mass as a factor in this product in order to get this correct answer of d sub f. Anyway, back now to part C. This is equal to 1/2 times the spring constant, which we calculated, 667 newtons per meter, times xa, which is 0.75 meters squared, and divided by mu sub k 0.350 times the mass 7.0 kilograms times g 9.80 meters per second squared. Then we stick that in our calculator and we find that the answer is 78.1 times 10 to the minus 3 meters. Or 7.81 centimeters. And that concludes this problem.